trying to do a retrosynthetic problem, so we call those retrosynthesis problems, meaning we have to work backwards and try to figure out this is the final product we want and this is our starting material. So kind of think a couple things we need to think about. This is just an alkane, so we're probably going to need to add, right, a bromine or some sort of leaving group on there, right? From alkanes, we only know how to really do the Br2 and light to get a bromine on there, so that's one thing to think about. Also, if we look forward, there's two things on here. So there's two new functional groups, a bromine and an O-methoxy. So we should think about how do we add two things. And also notice the stereochemical relationship. They're trans to each other. That should also tell you something as well. So the first thing I would do working backwards, if there's two things like this have been added, hopefully you recognize that this would have came from an alkene. This could have came from an alkene. We can add two things to alkenes. Now if we want to make an alkene, how do we make an alkene? Alkenes need to be made from, had to have a leaving group essentially. So this would have needed to come from working backwards, presumably having a bromine either that position or here. We could have either spot, just one. And then once you have the alkyl halide, that could maybe come from this. Now working in the forward direction, how do I add a bromine to an alkane? You need to use Br2 and an activator or light, initiator or light. And of course that adds it to the more substituted carbon, right? Adds to the most substituted carbon. Once we have the bromine on here, now we need to do an elimination. So we could do either an E1 or an E2 in this case, because even if we make a carbocation, it's not going to rearrange to something more stable. So let's do an E1, let's say. Large bulky base, and we're going to say maybe some heat. Heat's not that important. It is important, but minor details. So that gets us to a alkene. Now, how do I add a bromine and an O-methoxy? That's a tricky one, and they're trans. So if they're trans, you should remember something about bromonium ions. So you need to do this in Br2, and the solvent needs to be methanol. And the other byproduct here would actually be HBr. So that's our final product. That's the best way to do it. Now the question is, well, what happened? How does this work again? That's an old reaction. I haven't done that in a long time. What happens, and I'll just draw out maybe a generic version. If we remember this, drawing all our lone pairs, adds there. Number our carbons 1 and 2. What does our intermediate look like? We'd have a bromine that added, and we'd have Br minus. This would be an H, carbon 1 and carbon 2. We'd also have the other enantiomer of this, where the bromine not added from the top, but added from the bottom. But the other caveat here was there is methanol in the system. So OCH3. So that solvent, there's a lot more solvent around what's on the bottom part of the arrow, that's a solvent, than there is Br minus. So a solvent's actually going to react first, and it's going to react with the more substituted carbon, just like it does with epoxides in acidic conditions. So it attacks carbon 2. And of course, it does an SN2-like reaction, right? So the backside attack. So the product, where the O-methoxy, the O ends up, and the bromine are trans to each other. They end up being trans to each other. Right, so you can clearly see the bromine and the O are trans to each other, just like they are up here. A little different perspective. And then the last step is the Br just grabs the H, and that generates the HBr there. Key here is that concerted addition, bromonium ions like an epoxide, SN2 reaction, get the trans products. We've added two things across an alkene, and they're both trans to each other. Finally, just a special note, these problems are in chapter 18 at the end of the chapter. And they have hints and solutions. So they're very much worth taking a look at. These are the kind of problems that are when you're really kind of done studying, take a look at these. Like, you got to really kind of have a really strong grasp of all the reactions to do these. But for sure, take a look at the end of the chapter, not in the homework questions, actually end of the chapter. All right, so taking a look at a problem with an alkyne. So reviewing some of that alkyne chemistry about alkynes. When they're terminal alkynes, they're slightly acidic. Not because this bond is weak or not reactive. It's actually a really strong bond, the CH bond here. Right? There's actually a lot of orbital overlap there. But the product that you make is actually really stable. So putting a lone pair of electrons into an sp hybrid orbital, sp orbitals are close to the nucleus. The nucleus has positively charged protons, so it helps stabilize. Opposites attract. So how does this work? How do we actually deprotonate these? You need a strong base. So I showed a Grignard here, and it's going to act as a base now, not as a nucleophile. Right? It's a particular type of nucleophile. Right? A base reacts with hydrogen. This is one example. Another type of base that you've seen, maybe remember a little more, is NH2 minus, the NaNH2. That's one we use more in the first semester, a really reactive base. And what both of these will do is deprotonate and take off that CH, or take off that H, excuse me. This is a Grignard, so that's a carbon with a negative charge, carbon bonded to magnesium. This is methyl Grignard, we'd call it. So the first step is going to be this carbanion, which we could draw it like this and put the plus charge here. It's just a CH3 minus. What's it going to do? It's going to take that H and break that bond. 1, 2, 3. So that first step in the mechanism is going to be 1, 2, 3, right? Perfect. So the negative charge on carbon 1 that has the sp hybrid orbital, right? So that's why it's stabilized. And the other product, what's the other product we made here? Essentially, we made CH4, methane. Right? This was CH3, that carbon right there was CH3. It grabbed the hydrogen here. Now it's CH4. The magnesium bromide is there to balance the charge, so that is Mg+. So that's just to balance our charges out. All right? So what have we done here? We've taken the alkyne, we've made it very nucleophilic at carbon 1. And this is one of the examples of the nucleophiles I showed you for this unit were Grignards, organolithiums, H-, the hydrides, and then the other one which we knew before, right? We knew before was the alkyne, the acetylide anion, the negatively charged alkyne. That's a good nucleophile. Step 2 has a ketone, so that's going to react with the ketone. Where is it going to react with the ketone? The carbon of the carbonyl. That's where it's most delta plus. This is the carbon 1's nucleophile. The carbon of the carbonyl is the electrophile. We should number those carbons. Make this 4, 5, 6, 7. So carbon 5 is an electrophile. Carbon 1 is a nucleophile. A new bond to 5 to break the pi bond. That's that addition step. Right, we're doing an addition reaction. Right, we're adding something. What do we form when we do this? we form a, everybody with me now? Tetrahedral intermediate. We went from sp2 hybridized to sp3. And every time you make a tetrahedral intermediate, you ask yourself, are there any good leaving groups? Are there any good leaving groups here? What is a good leaving group? Something that could stabilize a negative charge. Is carbon stable with a negative charge? No. Is hydrogen stable with a negative charge? No. Would oxygen be? Yeah, oxygen would be better. Cl, chlorine? Yeah, right? Those are better leaving groups. Nitrogen, that's pretty reactive, probably not nitrogen. So we don't have any good leaving groups, so now we're done, right? Once we have a tetrahedral intermediate and there are no good leaving groups, we're done with that step. So step 3 then is, so this is just an addition. There is no elimination in this step. We just added something. So the last step, we're going to add in or react with H+. And so the final product is a tertiary alcohol. Let me try to number these carbons. So remember, we want bond to 1 and 5. Don't lose carbons. 1, 2, 3, 4, 6, 7. And we have a tertiary alcohol. All right. An alcohol is bonded, the carbon is bonded to 3 other carbons. Tertiary alcohol is the final product. This is the same mechanism, right? Doesn't change. Whatever the nucleophile is, it's the same kind of mechanism. Right? The first step is always the nucleophile attacks the carbon of the carbonyl in that addition step, whether it's H-, whether it's a Grignard, an organolithium, always the same first step. One thing to be on the lookout for, so if this is a ketone, if this had been an ester, there'd been an oxygen right here, and that would have been a good leaving group then. You would have added 2 of the alkynes then in that case, right? So you'd kick this out, you'd added 2. So be careful, check out workshop number 2, right? When you have an ester, things are a little different. You add 2 of your nucleophiles because the esters have a good leaving group. Quick review of E2 reactions. So eliminations are all about the sp3 beta CHs, as we remember. So here's one example. This has 2 leaving groups, 2 bromines, so we actually can do 2 eliminations. So we can form 2 pi bonds. So the final product here, if I give it away, is going to be an alkyne, 2 pi bonds. So carbon 1, carbon 2. Remember, in E2 reaction, things need to be anti-periplanar, 180 degrees away. So the difference in the wedges and hatches, I'm not going to worry about that right now, just because that just adds another layer of complexity to this that we're just not going to worry about, that you should know. We're not going to go there, though. So if we look at eliminating bromine on carbon 1, what do we need to look? What hydrogen do we need to take off to eliminate the bromine on carbon 1? Which hydrogen? Where is it at? On which carbon? It's on carbon 2. Right? The hydrogen on carbon 2. Remember, E2 reactions are concerted. They all happen in one step. This hydrogen and this bromine need to be 180 degrees apart. I'm not showing the stereochemistry here, but remember we talked about that anti-coplanar, anti-periplanar. This bromine and this hydrogen need to be, they're not right now, they need to be 180 degrees apart to make this actually happen. Because remember, that's the hybrid orbital, molecular orbital picture there. What's still bonded to carbon 1? What does carbon 1 have bonded to it? Hydrogen, how many? 2? What about carbon 2? How many hydrogens does carbon 2 have bonded to it? Just the 1. So now we need to eliminate the bromine that's attached to carbon 2. So which hydrogen should we take? Should I take hydrogen A or hydrogen B? B, right? Because again, we want things to be anti-periplanar, 180 degrees apart. Now we can see it a little better. If we had the wedges and hatches here, we would have seen it. Notice where the arrow goes, right between the bonds, showing that pi bond forming. And that leads us to our final product, 1 and 2, with these H's still there. Quick E2 recap, right? 1 step, 3 arrows, anti-periplanar, making pi bonds. All right, taking a look at quiz number 1, number 5. So quiz from this year, from 2018. We have an epoxide and an organolithium. That's step 1, and then step 2 we have H plus and acid. So the first thing we need to do every reaction, if we're kind of stuck, what's my nucleophile, what's my electrophile? So you have an epoxide and you have an organolithium. So if you can identify one, the other one must be the other thing. So which one do we know for sure is something? The organolithium, I mean, either way you could figure this out. The organolithium is a nucleophile. It's a carbon bonded to a lithium, a metal. That's going to be a nucleophile. We can even go so far as to redraw it, right, with a negative charge there and a plus charge here. All right. We should number our carbons. So that should be carbon 1, 2, 3, 4. So we've identified our nucleophile. What's our electrophile going to be? The carbons of the epoxide. Right, the carbons attached to the epoxide. Let's give them numbers. 5 and 6. Now the question is, are 5 and 6 the same or are they different? They're different. They're different. There's different substitution on them. One's more substituted than the other. 5's more substituted than 6. So we have a strong nucleophile. We have a negatively charged nucleophile. We have anionic basic conditions, negatively charged. Which carbon are we going to go for? What's the most important factor? Is it sterics or electronics? Sterics. So which carbon are we going to attack? 6. Very good. So you can show the electrons from there or the electrons from the bond. Go for carbon 6. You break the bond between carbon 6 and oxygen. Right? Be careful, make sure you break the right bond there. What does that give you? So you've opened the epoxide, so you have a new bond between carbon 1 and carbon 6. This is where numbering becomes really important. Don't want to lose carbons. Keep tracks. Okay, there's 5. There's 6. That's bonded to 1. 1 was bonded to 2. And then 3. Oh, I need another carbon. 4. Try that opened right. Broke the right bond. So I made a bond between 1 and 6. I broke the bond between carbon 6 and oxygen. And the only thing I'm missing now also is my lithium plus. All right, to balance my charge. So here you have it's kind of like a tetrahedral intermediate. Some level, right? Did an addition. We call this an addition reaction, right? We added something in. Is there anything else we need to do here? Well, this is not step 1. Step 1's done, right? So what's step 2? Step 2 is when we add in, right, H plus. Make sure we separate these steps. So what's my nucleophile? What's my electrophile here? Oxygen is a nucleophile, and H plus is always a great electrophile. H plus. There. Then the final product would be, what kind of alcohol is this? It's a secondary alcohol. That is correct. Again, number those carbons. Don't lose a carbon. Secondary alcohol. So now we have an alkene reacting with HBr, but not the normal HB, just HBr by itself, but HBr in the presence of peroxides. Right? The peroxide means 2 oxygens bonded to each other. It's a peroxide. So it's going to be different than normal HBr. Normal HBr, if it was just HBr, if I number these alkenes, or this alkene, carbon 1 and 2, bromine's going to end up on carbon 1, that Markovnikov product. Right? That's when we make a carbocation, right? The pi bond attacks, make a carbocation, the most substituted carbon, stabilized by hybrid conjugation, all that good stuff. And we'd get attack from both sides. This is going to be a radical reaction, so it's going to be a little different. So the first step in this reaction is going to be the initiation, right? The initiator breaking up. The peroxide, and there's two of them, breaks. And it is going to react first with HBr, another pretty reactive bond. What's that going to make? It's going to make Br dot plus ROH plus there's still another RO dot floating around as well. Okay. Now once we have Br dot, how's that going to react with carbon 1 and 2? So just similarly to a carbocation, radicals are electron deficient. So where would we rather have a radical on? Carbon 1 or carbon 2? 1, right? It's more substituted. So again, why is a more substituted radical more stable? Because of hyperconjugation, right? Those sigma bonds 2 bonds away can help stabilize it. So what's going to happen? So where's the bromine going to end up? Which carbon? 2. And the other electron from the pi bond goes to carbon 1. One and 2. Good. Okay. But obviously we're not going to stop here. So what's the next thing we need to do? We need to actually get rid of that radical. So we can use, let's say there's more HBr in the system. We need to get that H, right? We need to get that H on there. So that's going to happen. And now we're going to make Br dot again. And what else are we going to make? What's the other key difference here? When that H becomes bonded to carbon 1, is that H going to come from the top, the bottom, or both? What's the hybridization state of a radical? sp2. What's the geometry of an sp2 hybridized atom? It's planar, right? So as a p orbital, so the hydrogen can come from the top or the bottom. So what does that mean? Does that matter in this case? It does matter, because carbon 1 carbon 1, carbon 2. Carbon 1 here has how many things bonded to it? How many different things bonded to it? 4 different things bonded to it. That's correct, right? What hybridization state is it? sp3. It's an asymmetric center. So when this hydrogen added in this step, it could have came from the top or the bottom. So we need to draw wedges and hatches here, because we get both enantiomers. Also, everybody noticed along the way, there's been a stereocenter. So what did we just make? Do we make enantiomers, diastereomers? We made diastereomers. So if we only had if we were only making this one stereocenter, it would be a racemic mixture. But since this never changes, let's see what they look like. So the H here could be down, or the H could be up, right? Carbon 1, carbon 2, carbon 1, carbon 2, right? This asymmetric center stays the same in both cases. This one changes. Those are not enantiomers, those are diastereomers. Remember, diastereomers are molecules that share one stereocenter. At least one is the same, and everything else can be different. So one is the same, one is different. These are diastereomers.
So the bond between carbon 1 and 2 would become wedge or hatch?
No, the bond between carbon 1 and 2 is wedged or hatched. I said you don't necessarily have to draw it. So in this case, I would draw it as wedged. In this case, I would draw it as hatched. I was just trying to emphasize the hydrogen is really the key, right? Key from this step coming from the top and the bottom. Yep. Yeah, if you have wedges and hatches, right? So for this one, then the H that's on here has to be hatched, right, in both cases. Sometimes we just don't draw both things in, but it's always there. Question number 1 from quiz 1 from this year. Let's take a look at the mechanism to do a reduction of a carboxylic acid with lithium aluminum hydride. The reduction of a carboxylic acid with lithium aluminum hydride. Aluminum aluminum's lower on the periodic table than boron, so sodium borohydride is the other hydride source you're used to. This is more reactive because aluminum's larger, so the bond is more reactive because there's less orbital overlap. And I replaced the hydrogens here with Ds, so deuteriums. So it's just hydrogen with an extra neutron. That's all it is. So they react pretty much the same way. So the first step here is going to be my nucleophile is going to be a deuterium, right? The negative charge is on the aluminum, but where is the electron density actually at? On the Ds, or the H would normally be H's. Right? That's where the electron density is, because this is still a metal. Remember, the negative charge, just because where the charge is at, that can lie to us, remember? Right, so the actual electron density is on the D's or the H's normally. So this is going to be my nucleophile. This is a carboxylic acid. Where is the carboxylic acid most electrophilic? Got to be careful here. Is it the carbon of the carbonyl, like all the other ones? Or do we remember that it's an acid? We remember that it's an acid. Carboxylic acid. It's going to react like an acid first, right? So it's different than ketones, esters, and aldehydes. The first step, one of the deuteriums reacts with the H bonded O, like an acid-base reaction. And what does that make? It makes the O minus. And we've also made hydrogen, essentially H2 gas. HD gas, I guess, as it were. The aluminum's still around. And so is the lithium to balance our charge out. So the next step, right, is going to be a little interesting. So you drew it actually probably, I would argue, maybe a better way on the quiz than they did in the book, but I'll show you the way the book has it. Essentially, this pi bond is going to need a break. We're going to keep, essentially the idea here is we're going to keep reducing this carbon. We need to add hydrogens to this carbon. If you notice when we did these reductions, we're always adding hydrogens. Oxidations, we're adding oxygen bonds. The chromium, you take an alcohol and make it a carboxylic acid. So you added more bonds to oxygen, oxidation. Reduction, you take away bonds to oxygen. You add hydrogens as a reduction. So in the end of the day, we're doing a reduction with hydrides. So we need to add hydrogens here, or Ds as it were here. So what's going to happen is when the deuterium is going to go for the carbon and the carbonyl now. Now you're used to that, the carbon and the carbonyl. And this pi bond is going to break, but instead of just going to the oxygen, it's actually going to go right to the aluminum. Think of it this way. Who knows the mechanism this looks like? Anybody see it yet? We've seen a mechanism just like this. BH3. The BH3 mechanism is just like this, right? Except it's aluminum H3 or aluminum D3, where the aluminum goes on the less substituted spot. This is like a pi bond, right? Just now it's not an alkene, it's like carbonyl, but it's the same exact mechanism. If you think about it, it's a syn addition, right? The aluminum ends up on the less substituted position of the pi bond. So it's the same. You've seen this before. Whether you remember it, that's a different question. So what do we do? We had sp2 hybridized. Now we have sp3 hybridized. Right? It's sp3 hybridized. We added a D deuterium, or it would have been an H minus normally. and the oxygen and aluminum are bonded to each other. What does this look like to you? This was a sp2 hybridized. Now this is a sp3 hybridized. It's a tetrahedral intermediate. If you have a tetrahedral intermediate, what do you ask yourself? Is there a good leaving group? Is there a good leaving group? Yeah, oxygen, this whole thing can just leave. Great. So this was like an addition. We added something. And now this step, of course, is a elimination. We're making a pi bond. So a 1, 2, 1, 2, just to see where we're at. So this is like an aldehyde, right? Essentially like an aldehyde. And the other thing we made was the O- aluminum bond to these. So far, so good. So the way I set this up might actually not be possible, but this is the way I set up the problem. Then I said, okay, stop right here. And I said, now you're going to add in somehow we're going to do this. We're going to somehow take this and now add in lithium aluminum hydride. So instead of having D's now, it's going to have all the H's. So now what's going to happen? Instead of adding D's, we're going to add an H, right? So we're going to do an addition reaction. So normally what would happen, if I hadn't like forced you to do this, this would keep reacting with this, right? We'd add another D. But in my hypothetical situation in your quiz, I made you stop. Normally you would keep reacting. It should keep reacting. But I stopped it on the quiz. All right, everybody see that? So now we'd have tetrahedral intermediate. Are there any good leaving groups? D is like hydrogen, so no. Right? There's no good leaving groups. So now we're done. So the second step was step 2 was H plus. So the final step is this, just grabbing that H. And the final product should be a primary alcohol with an H and a deuterium on that carbon. Really important to remember though, right? Normally this would just keep reacting. This would just keep reacting. Wkshp number 2, carboxylic acid reacting with a Grignard. So again, carboxylic acid is the ones that trip us up. Grignard is going to be a nucleophile or electrophile. Nucleophile, and it's nucleophilic at this carbon. So if I number these carbons, 1 and 2, it's like a carbanion, negatively charged carbon. So that's my nucleophile. That means this is my electrophile, this carboxylic acid. So there's 2 places it could be electrophilic, the carbon or the carbonyl, but we always remember it's a carboxylic acid, and it's an acid first. This is the most electrophilic site, the hydrogen. So what's going to happen with a Grignard in the presence of an OH or NH, right? This is one of those the Grignard feasibility question. Grignards can't, right? They only react, they're going to react with OHs and NHs, pHs and SHs. Any of those heteroatoms with the hydrogen, they're going to react with it first. That's why Grignards aren't compatible with acid, right? Grignards are not compatible with acid. A negatively charged carbon and acid, it's just going to react with that H+. So that's the problem here. So what's going to happen? That bond breaks. And this is different than the lithium aluminum hydride, because now what have we done? We've made this. We made a gas. right? Because there's hydrogens on those carbons. And we have MgBr plus. So even if we had more Grignard around, is this very electrophilic now? What, all of a sudden this has a negative charge. Do electrophiles usually have negative charges? No, they're electron deficient. So this is going to have lots of resonance. And what's that resonance going to do? It's going to make this carbon less reactive. So now we're stuck here. This won't react with the Grignard because now they're both kind of nucleophiles. And this is also stabilized by resonance. So you're kind of done. So nothing can happen, right? You can't have two nucleophiles react. So all that happens now is that goes against the H, that's step 2. And what do you end up with? You start right back in the same starting material. You actually end up with the same thing. That's why you got to be careful which kind of things you choose to react your Grignards with. Grignards won't work with acids. They'll react like an acid-base reaction.